Welcome everybody to this edition of Exail. My name's David Cunningham and I'm in Saint-Germain-en-Laye at Xblue's headquarters in France. I'll be your host for the day, or for this session. We're going to talk today about Sparse LBL and dig into some of the concepts and the techniques around that positioning methodology. I'll be joined shortly by a colleague of mine from our facility in Brest. The order of the day will be as previously, around about a 15-minute presentation, followed by questions and answers. So we want your questions and we'll give you answers. So please, during the course of the presentation, don't hesitate to post any questions you may have on the right-hand side of the web platform. And we will do our very best to answer them all before the end of the broadcast. We'll probably provide an FAQ document available on our website after the event, along with a recording of this broadcast. So what I will do now is introduce you to my colleague Pierre-Yves Morvin, who's, as I say, based down in Brest. He's the product manager for our subsea positioning product line. So welcome, Pierre-Yves.
Hello, David. Hello, everybody. Thank you. I'm glad to be there and to have the opportunity to talk about Ramses and Sparse LBL.
Yeah. Okay, that's great. So what we'll do, as I said before, we're planning to talk a little bit about Sparse LBL. And maybe what you could do, Pierre-Yves, is just very, very briefly, just give a context of the ecosystem, Xblue's kind of ecosystem for endeavoring to do Sparse LBL.
Yes, so Xblue positioning offer for subsea navigation is composed of several bricks. So one of these bricks is our USBL system, GAPS series, composed of GAPS M5, recently introduced on the market or recently developed, and GAPS M7. So this is for USBL. Then we have INS, a range of INS, fins, Rovins or Rovins Nano. We also have a LBL transceiver, which is Ramses, that works with Canopus transponders, so the transponders which are on the seabed. And we also have a software suite. The name is Delft Subsea Positioning.
Okay, so that's the building blocks for attempting Sparse LBL, and I'm joined on the set here by a Ramses transceiver and a Rovins Nano. So what we're talking about here is something you can develop with any Xblue INS, whether it's a Rovins Nano, fins, or a Rovins. So what do we need to actually embark on Sparse LBL?
So what you need to do Sparse is an INS and a DVL, and on the vehicle also a Ramses transceiver. So it will be the LBL transceiver that will interrogate beacons on the seabed. So these beacons has to be calibrated if you want geo-referenced positioning.
Mm-hmm. Okay, so we're going to use INS Ramses fitted to the vehicle with and at least one beacon deployed on the seabed. So what are the objectives then with this Sparse LBL? What are we trying to achieve?
So the objective of Sparse is to reduce the number of transponders that you have to deploy on the seabed. So Xblue system enables Sparse from one single transponder. And the objective, of course, is to reduce the cost of deployment, the time required for the calibration of an LBL array, and also reduce the cost of maintenance related to the battery replacement of the seabed transponders.
Okay, so that's what we're trying to achieve, and now you can perhaps describe how that's possible.
Okay, so if I focus on Ramses principle is quite simple actually. Ramses transceiver will interrogate a transponder on the seabed to measure the range to this transponder. And then Ramses will feed the INS with this range associated to the position of the transponder. And the key word here is the Kalman filter that runs into the INS. The Kalman filter is the heart of the system and will merge all available information from various sensors to make the navigation of the vehicle. So it could be a position coming from a USBL, a speed coming from a DVL, but also a range coming from the Ramses transceiver. So the Kalman filter takes everything that has a link with the positioning, of course, and combine all this information to provide in real time the best possible estimation for the position of the vehicle.
Okay, so at the heart of the positioning solution is the Kalman filter running in the INS, and it's using input from various sensors. Maybe you can just describe in practice exactly how this Sparse LBL works.
Yeah. So as you can see, or as you will see on the screen, we can consider that initially we have the INS is estimating a position and a standard deviation. So the standard deviation and the position are represented by this blue circle on the screen. So this is the initial state of the Kalman filter, I would say, or the INS position. Then the Ramses will measure a range to a transponder, which is represented here on the right part of the screen. So the Ramses will transfer this range to the INS, and the INS will be, or the Kalman filter will be able to update the error ellipse and to make this error ellipse very thin in one axis, at least, in the axis which is perpendicular to the direction of the transponder. Then the vehicle will make its own route and will have a different angle to this transponder. So we will not only have a good accuracy or a good knowledge of the position on one axis, but we will start to also observe the second axis. And at the end of the day, we at the end of the navigation of the AUV or ROV, we have a very good estimation of the positioning of the vehicle on all axes.
Mm-hmm. Okay, so that could be a relative position or a real world position, depending on the arrangement. But basically, the Ramses is going to continuously interrogate the single beacon, which is gradually narrowing and narrowing the error ellipse. And as it changes angle relative to the beacon, we close the error in positioning right down, just with one beacon. So, what are the advantages then of this technique?
So the advantage of using a Kalman filter is first that using 1, 2, 3, or even 10 beacons doesn't make any difference for the computation and for the algorithm. Mm-hmm. So this is the first difference. And also we can say that we don't need, imagine you have several beacons on the seabed. We don't need to interrogate all the beacons simultaneously. We can sequentially interrogate each transponder and save the battery and increase the autonomy of the transponder. Okay,
so we can work with minimal beacons and we can interrogate them sequentially. So we're not needing a simultaneous measurement to multiple beacons, which makes it very much more efficient in terms of battery life. So then, what about when will we use Sparse LBL rather than USBL or a conventional LBL methodology?
Okay, I think we can say that USBL for some application is not accurate enough. Typically, in 2,000 meters of water depth, you will get 4-5 meters accuracy with a USBL. So sometimes it's not enough. And at the opposite, LBL is very accurate, but it's quite a complex system in terms of the number of transponders to deploy and so on. You can reach 10 centimeters accuracy, but it's quite a heavy system, I would say. So Sparse will provide a positioning accuracy which is in between the USBL and LBL. So Sparse, we will see later that with Sparse, you can easily reach 50 centimeters accuracy with 1 or 2 transponders on the seabed.
Okay, so the idea is it's going to fit between USBL when USBL becomes insufficiently accurate, and when, let's say, LBL is cost or time prohibitive, then we can solve some measurement problems roughly in that sort of area with this technique. So regarding calibration of transponders, Pierre-Yves, what are the options there?
Yes, so it's a good question because with classical LBL, you run a box-in from the surface on a few transponders of the LBL array, and you also run a baseline calibration. Baseline calibration means to get the direct ranges between the transponders. With Sparse, by definition, the range, the distance between transponders is quite important because you want to reduce the number of transponders that you deploy. So we cannot use these techniques. But we have the capability with the Ramses to run the SLAM algorithm. So SLAM is a calibration technique to quite quickly estimate the position of the transponder and to calibrate it. So the principle consists in making a navigation with the ROV above a seabed transponder. So a 10 radius circle, 10 meter radius circle above a transponder. You run your SLAM, so it means that you collect the range to this transponder. You also collect USBL fixes, and the INS and the Ramses will calibrate the seabed transponder.
Mm-hmm. Okay, so if we want to get real-world positioning and secure that, then we need to position the beacons. We can do that from the surface or from the ROV. We can use SLAM techniques, very powerful. And I think we've done some of this type of work already with DRIX, for example, in the Caspian Sea. So Xblue has some other tools in the toolbox to help to do that efficiently. So moving on now to applications, Pierre-Yves. What about just very broadly? What are the application areas for this Sparse LBL technique?
So any vehicle navigation. So we can talk about ROV navigation, AUV navigation, and towfish navigation. So Canopus technology and Sparse LBL is really adapted for ROV, for example, ROV navigation, because the combination of acoustics and inertial makes at the end a very robust positioning with very high update rates. So this is typically what needs a ROV pilot, a robust positioning with high update rates.
Yeah.
And AUV and towfish, the main advantage of using Sparse is that you will cover large areas, and this is the purpose of AUVs and towfish. You will cover very large areas with a minimum of transponder.
Mm-hmm. Okay, so basically it's ROV navigation, AUV navigation, and potentially some towfish applications. Really, anywhere you've got an Xblue INS, so whether it's a Robbins Nano, a Fins, or a Robbins, we can deploy this technique very simply just by adding Ramses and a beacon. So what sort of performance can we expect from a Sparse LBL solution?
So to give an overview of the performance, I would summarize by saying that with a single transponder, you can get 50 centimeters accuracy, so 50 centimeters. By adding a transponder, so by navigating with two transponders, you can reach 20, 30 centimeters. And with three or more transponders, then you get pure LBL positioning accuracy, which is around 10 centimeters. Mm-hmm. So I think you will see a graphic on the screen showing the performance that we can get. So on the left of the screen, this is a simulation. So a simulation run with DSP, so Delft subsea positioning. So this graphic is showing a trajectory for a vehicle. This trajectory has been described yes in DSP. And DSP enables to place transponders on the seabed. So on this example, we have a single transponders on the northwest of the trajectory. And this graphic is representing with colors the positioning error all along the simulated trajectory. So when you have a color which is around the blue or green, it means that you are below 50 centimeters. And this simulation is showing that positioning accuracy is always below 50 centimeters. And on the right part of the screen, we have same kind of data, except that this is real data. We conducted trials, sea trials with surface vessel. We deployed the Ramses transceiver, the INS, and the DVL on this surface vessel that was also equipped with RTK GNSS. So we were able to compare the GNSS with our positioning solution. And what is really interesting to see here is that both graphics are showing the same error. So it means that we have a very good tool, a simulation tool, that enables our customers to not spend hours at sea to just answer the question, how many transponders I have to deploy on the seabed, where I have to deploy on the seabed to reach a certain positioning accuracy.
Okay, so in a nutshell then, one beacon, one seabed beacon gets you 50 centimeters, two gets you around about half that, 25 centimeters, and three or more gets you LBL performance at sort of 10 centimeters. That's the ballpark figures. And the simulation, the power of this Delph subsea positioning simulation tool allows you to model the navigation performance before you put to sea. Maybe you can just tell us a little bit about how that works, Pierre-Yves, just a bit more detail about how the simulation, what's the input?
Yeah, so the inputs for Delph subsea positioning simulation module is first the bathymetry or the digital terrain model. So you input this into the software. You also input the sound velocity profile, which has an impact on the acoustic propagation, of course. Then you will place the transponders on the seabed, as many as transponder you want, and you will also describe the vehicle trajectory. Then this software will build or will synthesize a post-processing file, an inertial post-processing file that you can import into Delph INS, and Delph INS will tell you what will be the standard deviation during the navigation of the vehicle.
Okay, so so we're able to model any given scenario and give a clear sort of understanding of what the likely performance is in the real world. So that's broadly the end of our presentation, Pierre-Yves, I think, and we've got I can see a lot of questions brewing. But basically, so in a nutshell here, we're talking about Ramses fitted to a vehicle which has Xblue INS, whether it's fins, Rovins or Rovins Nano, and a minimum of one beacon deployed on the seabed. Could be a relative position. It could be you could box it in and get a real world position, and then we can use this technique. So questions. So the first question is, can you tell us a little bit about who's using this technique already?
Yes, I can say a few words about Ifremer that recently qualified this technology for the navigation of their vehicle. So Ifremer is having several vehicles, AUVs, ROVs, manned vehicles also. And they conducted recently sea trials, quite deep, 2,000 meters, more than 2,000 meters, to completely qualify this technology for the navigation of their vehicle.
Okay, yeah. So there's obviously the ocean science community can make benefit of this technique, as well as maybe the subsea construction applications. So here we've got one about transponders. What's the range of our transponders, Canopus transponders?
So nominal range of the Canopus transponder associated with the Ramses is around 4 kilometers. But it's important to say that in the real world, the limitation, and mainly when you are deep, the limitation comes from the sound velocity profile. So in 2,000 meters of water depth, for example, we can get a range of 1,000 meters, like a classical LBL system, I would say.
Yeah. So moving on, another point about transponders. how can we configure transponders? Is there a way to do that in a sort of batch processing way or wirelessly?
So today we still need to configure the transponder with a physical link, but all the transponders, the hardware which is manufactured now is compatible with Wi-Fi connection. So we still have to work on the firmware, but the Wi-Fi configuration of the transponder and the configuration of a batch of transponders will be available in a few weeks or months.
Okay, so it's they're Wi-Fi ready, but for the time being, it's necessary to have a physical link with each beacon to configure it. So here's another one. What's the minimum number of LBL transponders required for Sparse LBL?
So I think we answered. One transponder enables to reach 50 centimeters accuracy when you are in the acoustic line of sight of the transponders. 2, 3, then you get 25. 2 transponders, you get 25 centimeters, and 3 transponders, you get 10 centimeters.
Yeah, which leads quite nicely on to this next question, which is what happens in case of masking of a transponder by a structure or the terrain?
Yeah, this is very interesting question because I come back to my explanation on the Kalman filter. The Kalman filter will take what arrives, but if a range is not arriving during a few seconds or even a few minutes, the INS and DVL navigation will still run. And after a few minutes, you still have a very good positioning accuracy with INS DVL navigation. So as soon as range will come back, as soon as you will retrieve your acoustic line of sight with the transponder, then the Kalman filter will be updated with this range, but it will not change anything to the previous navigation, which was already quite accurate.
Yeah. So the point is that the technique can manage without continuous updates from the acoustic beacons, and so masking is well, may or may not be a problem if it's masked continuously. Obviously, you're no longer getting any benefit from the ranges, but if it's just occasional, then it's not going to be a problem. So we've got another question here about accuracy, which we've answered previously, but please answer again in case the person who's asking has only recently joined. What level of accuracy could we achieve using SLAM techniques for LBL transponder position on the seabed?
This is a good question because if I understand the question, this is related to the calibration of the seabed using ROV and USBL. So I was saying earlier that with a USBL in 2,000 meters of water depth, for example, you can get 5-meter accuracy. So we will use these positions to calibrate, to perform the SLAM and to calibrate the beacon, but we will average the noise which is in this positioning, in this USBL positioning. We will average the noise by making a circle and by using the INS DVL navigation. So at the end of the circle, I think we can divide by at least 5 or 10 the immediate, I would say, USBL accuracy. So if I come back to my 5 meters, we can SLAM a beacon with 50 centimeters accuracy in 2,000 meters of water depth.
Okay. Yeah. So we make enough measurements, and we can obviously get the position right down. So here's another one. How important is it to select the type of INS to improve the SLAM? Does the performance of the INS affect the accuracy of the SLAM measurements?
No, I wouldn't say that because when you have a USBL on your vessel and that you feed your INS with this USBL, any INS, it can be a FINS, a ROVINS, or a ROVINS Nano, will provide the same navigation performance.
Okay.
I would say that you require a FINS when you really need an accurate heading and when you plan to make a navigation without LBL aging and range aging. So in that case, if in the scenario you have these long periods of fins DVL navigation, then you need a fins.
Okay, yeah. So, but in order to use the SLAM or get the best performance from the SLAM, it's not dependent on the quality or the grade of the INS. So here's one about post-processing, and can I operate and/or process using third-party software?
Third-party software, no, I wouldn't say that. But I can say about compatibility with third-party systems that we are developing the compatibility with third-party transponders. So the Ramses will be able to interrogate third-party transponders. We will be able to calibrate the transponders with third-party USBL. And yeah, that's it.
Yeah, okay, yeah. So we've got one final question here, I think, which is about training. And so the question is, where can I get trained?
Yeah, good question. So I would like to say anywhere. So we have a training center in Aberdeen for people who want to physically be there. We can also do webinars, so spend a day on DSP software, for example, and train people remotely. And of course, we have a pool of support engineers that can go anywhere in the world and support and train people on the vessel.
Okay, yeah, so flexible, very flexible in terms of training. We can, you can come to us, we can come to you. Or we can indeed do it remotely with tools like this. So we've got a worldwide support team who are ready and able to deliver that training wherever you might want it. So I think that's all we've got time for. I think we've run out of questions. So thank you very much, Pierre-Yves, for joining us today and giving us a bit of an insight on Sparse LBL.
Thank you, David, and thank you, everybody. Thank you to the audience for attending this presentation. If some people want to continue this conversation, then they will find my details on XBlue website. So thank you and bye-bye.
Okay, well, thank you very much for joining us with this broadcast here today. I hope you learned a little bit something about how we manage Sparse LBL. If you want to learn more, don't hesitate to contact XBlue. And if you want to contact Pierre-Yves in person, you'll find his details on our website. We will be posting a recording of this on our YouTube channel and on our website after the event. So if you want to relive the experience or show it to colleagues, don't hesitate. We will be doing more XLive broadcasts in the coming weeks and months. So please stay tuned to see the schedule for those. And in the meantime, thank you very much for attending, and we'll hopefully see you again soon. Goodbye.